All right, hello everybody, and thank you for coming. My name is A Bunch of Square Boxes, and I'm here to talk to you about square boxes. Wait, no, that's not right. My name is James McNellis. I'm a member of the Visual C++ team at Microsoft, where I work on our C and C++ standard libraries, amongst other things. And I'm here today to talk about Unicode in C++. The bulk of this talk is actually going to be about Unicode and text encoding, and then toward the end we'll talk about how things are done in standard C++ using the standard C++ library, but also using a few other libraries. A few caveats before we begin. Anywhere we say byte, we mean an 8-bit byte or an octet. We're not talking about any of these crazy systems, or some people have a very abstract idea of what a byte is. Sometimes when you get C++ standards experts, they like to nitpick on things like that. Most of the numbers in the talk are hexadecimal, but I've omitted the 0x just to save space on the slides. And we're going to keep this kind of high level. We're not going to go into a lot of the nitpicky details, but we do want to explain thoroughly how Unicode works and how it's used in C++. I have a lot of slides to get through, so we'll probably save questions for the end, but if you have something really pressing, feel free to raise your hand. So, Unicode began as a project in 1987. So what did we do before we had Unicode? Obviously we had to encode text somehow. It wasn't like before that all we had on the computers were numbers. So let's consider how we represent text in a computer to begin with. And the first thing to start thinking about is, well, if we only have a small number of characters, we can store 1 character per byte, and this works very well for English. So I'm sure everybody here is very familiar with the ASCII character set. It stands for the American Standard Code for Information Interchange. It has these lovely 95 printable characters. One of them is the space, which is probably not visible on the slide. This is great for English. You can represent basically all of English using these characters, plus we have a few extra special characters for punctuation and things like that. It's also a very simple encoding. So for example, here is the string hello. These are the characters, H, E, etc. And in order to encode it in ASCII, we basically map each of these characters to a numeric value. So the H gets mapped to 48, the E gets mapped to 65, etc. A few pieces of terminology to note here. So here, the characters are like the abstract things. So the letter H, the letter E. It has nothing to do with the font, so we could use a totally different font up there. And then the numbers, the numeric values, are called code points. So we have a unique mapping of each character is represented by a single code point. And it works both ways. So if we see a 48 in a file and we're parsing it as ASCII text, then we know that it's going to be the capital letter H. The other term that we need to know is code units. So here in ASCII, each code unit is 1 byte. So 1 byte is our fundamental unit in the text. Turns out ASCII is a little different than that, though. ASCII is actually just a 7-bit character encoding. So if you're encoding 1 byte per character, then the higher order bit will always be 0. In addition to those 95 printable characters, it also has 32 control characters. The best known of these would be the carriage return and line feed, but there's a bunch of others that are less frequently used. ASCII is near ubiquitous, for single byte character set, and it's great for English, but not so great for most other languages. Like even German, there's some characters that we need that aren't that we can't represent in ASCII. So since ASCII is only a 7-bit encoding, we kind of have 2 options for doing some fun things with it. So one option is we could use the extra bit for parity, which is actually what it was used for in the beginning. We could compress the character stream together, so we could actually fit more than 1 character in a single byte. We can use that extra bit to store part of the next character. Or we can extend it. And so we can use those extra 128 code points at the high end of the single byte range to represent more characters. And so these are a bunch of extended ASCII code pages. So the IBM code pages, there's a bunch of them. Mac OS had a Roman code page and others like that. And so here, for example, are the extra characters you can represent using code page 437. This was the default character set for the original IBM PC. In addition to all of the ASCII characters, we can also represent all of these. So we can represent a whole bunch of other languages, or most of a whole bunch of other languages using these. Since this was for the IBM PC, which primarily used a text interface, we can also draw some nice fancy borders. It's got some Greek letters for mathematical symbols and things like that, which might be useful for spreadsheet software. But this is just one example. So there's many ASCII-based encodings that do different things with that extra bit. And there was actually an ISO working group or committee, ISO IEC 8859, And they defined a whole set of encodings that were based on ASCII. So again, the bottom 128 code points were all the same as in ASCII, and then the high 128 code points were different depending on which encoding you were using. This ISO group has disbanded. They're doing no further work because Unicode is the new standard, but we're not talking about Unicode yet. And the sets of characters that they chose for each of these was based on commonly used typewriter keyboards in different countries. So they really tried to match like how people were actually writing text before computers, basically. So the first one of these is Latin 1. Latin 1 covers 29 languages completely and a bunch of other languages mostly completely. Languages that it covers completely include German and Danish and Italian and Spanish. For a few other languages like French, Finnish, Estonian, there's another encoding, Latin 9, that's required. Latin 9 also adds the euro symbol, which didn't exist back when Latin 1 was first specified. And Unicode is based on Latin 1, and we'll see that in a bit of detail later. But that's just one example. So for example, if you're writing in a language that needs Cyrillic characters, you might use the 8859-5 encoding, or Latin/Cyrillic. And this lets you represent, for example, Russian. So here we can see an example of just how these encodings work. So this is the Russian word for hello. And we can see that we map them to their code points just like we did with the ASCII. So because each of these are Cyrillic letters, they all have the high order bit set. That first hexet is always greater than 8 or greater for all of these. And so we can see we just simply map them to their code points to encode. And decoding works in exactly the same way. So if we have this byte string in a file, we can decode it using this code page to get our string back. But the problem is that there's many 8-bit encodings, and so you have to be sure that we use the right one. So for example, if you're in Russia and you write this hello message to a friend of yours who happens to live in Greece, and he's using the ISO IEC 8859-7 encoding, which is the Greek encoding, then he's going to decode it and he's going to get this gibberish. I'm sure that many of us have had some occasion where we've opened a file and it doesn't have the contents we've expected, or sent an email. It's getting less frequent nowadays now that we're using Unicode, but with older systems this was somewhat common. So these single byte encodings, there's many nice properties. Every character is the same size. Each character requires a single byte to represent. It's compact, so we're not wasting a lot of bits. Even if we're just writing English text and we don't need, we're at least using 7 of the 8 bits in each byte, and so that's still pretty compact. String operations are generally straightforward, right? We can iterate over each element in the string, and each element is going to be a single character. But it's got this giant downside that there's not enough code points to represent all of the characters. So one option to fix that is we can use different encodings for each character, or that can be used to represent different sets of characters. But that does not work for all scripts in all languages, right? So for example, there are Asian languages, Chinese, Japanese, Korean, that have a large number of characters, more than the 256 that we can represent using a single byte per character. And so these single byte encodings, they make text interchange difficult. So the first solution, if you will, to this are variable length encodings. So if 1 byte is not enough, how about we start using multiple bytes? But let's say we don't want to break compatibility completely with ASCII. What can we do? So we can use variable length encodings. Another name for these is multi-byte. They're called multi-byte in the Microsoft implementation. And a very common example of this is ShiftJIS. JIS stands for the Japanese Industrial Standards, and ShiftJIS is a variable width character encoding used to represent many different languages of characters, but especially the Japanese characters that are needed for Japanese text. So some characters are representable using a single byte, and others require 2 bytes. When we have 2-byte characters, they consist of a lead byte, which will be followed by a trail byte. And so if you find one of those lead bytes when you're scanning text, you have to then read the next byte, put them together, and then look it up in a table, and it'll tell you what the actual character is that's represented there. So it starts with 7-bit ASCII. It makes a couple of substitutions. It replaces the backslash with the yen symbol, for example. And unfortunately, this encoding is very complex due to overlap. So here's a picture of the table. So here in the table, the yellow and blue characters are representable using a single byte, so those include all of the ASCII characters. And then the red characters, the red boxes on the left-hand side, are lead bytes, and so if you're parsing along and you see one of those values, you then need to combine it with the next byte to figure out what the character is. And so here's an example. So if you're reading a text and you come across the value 44, well, that's the Latin capital letter D. It's just like it is in ASCII. If you come across an 84, though, that's a lead byte, and so you then need to combine it with the next byte. And so if it's a 44, then it would be the Cyrillic capital letter day. If it's an 84, then it'll be the Cyrillic capital letter te. Here's just an example of this. So for example, we read the 44, it's a D, we read another one of those, and then we read two of the multi-byte characters, and then we read another multi-byte character. So one problem here is that this byte 84 can appear as either a lead byte or a trail byte. So if you have a pointer into a string and you're not entirely sure whether you point to a lead byte or a trail byte, it can be very difficult to A, synchronize yourself with the string, so find the beginning of the next character, or B, go backwards to find the beginning of the current character that you're in. Because here, is this character is this byte that we're pointing at, is it a lead byte or a trail byte? I don't know. And you may have to actually walk all the way back to the beginning of the string and then scan forward to figure out what that pointer is pointing to. So this Shift.js encoding is just one technique. There are others. Another common technique is to use escape sequences to switch between working sets of characters. So for example, you might be using ASCII, and then there will be some escape sequence, and that'll tell the text processor, okay, the next block of text is going to be in this other encoding. It's going to be this other character set. And then when you want to switch back to ASCII, there will be another escape sequence that you'll use. So ISO IEC 2022 is an example of this. These encodings are even more complex because you need to maintain state when you're iterating through the string, because you have to know what your current escape status is. So multi-byte encodings, we get a substantially expanded code space. Even if we want to maintain compatibility with ASCII, where we still have those single byte characters, we can represent up to 32,000 characters. I mean, that's a lot of characters. Though real-world encodings tend to have lower limits just because of how they're designed. Some byte-oriented string operations still work. So for example, if you want to use strcpy to copy a string, that will still work with these. But they have a bunch of disadvantages. They're complex to parse. In some cases, it depends on the particular encoding. Some common string operations may require a linear scan over the string, like the example we saw just a moment ago. Many simple string operations become difficult or require special APIs, like if you want to get the previous character or a pointer to the previous character, you can't just decrement the pointer, you need to actually go and find the lead byte. And then we still have the problem that there's many different encoding standards. So we didn't actually solve that problem, which is really a really important problem to solve for text interchange. So, Unicode. We're going to first look at Unicode 1.0, so how it was originally designed, what the original design was, and then we'll jump forward and we'll look at what it looks like today. So given that 256 characters are not enough, and multi-byte encodings are a pain to work with, instead of using 8 bits per character, let's use 16. So 65,000 characters ought to be enough for everybody. So the name Unicode originally derived from unique, universal, and uniform character encoding. So that's a lot of UNI, prefixes for those words. And it had a few design goals. It was designed to be one character encoding to rule them all. So they wanted to have one character encoding that you could use to represent basically any text, so that you didn't need to worry about the encoding of the text when you're sharing it, between systems. It was designed to be universal, so it should be able to represent all the characters likely to be used in text interchange, so that includes all of the different alphabets and scripts that are used in different languages. And nowadays, it also includes very important things like emoji. It's also designed to be efficient, so plain text should be simple to parse, and unambiguous, so any given Unicode code point will always represent the same character. So if you have a numeric value, you can always map that one-to-one with a particular character. And finally, again, this is still a set of characters, not glyphs, so we're not concerned with the visual representation. So we're concerned with the abstract idea of the letter A, not the particular font or the particular way of rendering it. So in Unicode 1.0, each character is mapped to a 16-bit code point. Up to 65,536 characters can be represented. In theory, it's fewer in practice. All of the characters in ISO IEC 8859-1, so that Latin 1 encoding, map to the same code point. So if you have a Latin 1 string and you just convert each of those 8-bit elements into a 16-bit element, you have a string in Unicode that represents the exact same set of sequence of characters as you had in the Latin 1 string. And the encoding that was used here for Unicode 1.0 is called UCS2, and basically it just means that, says that the each code point, each character value is mapped to whatever its value is in 16 bits. So here's our hello example again. This U+ is just the standard way of saying the Unicode character with this particular code point. So we can see that H maps to 48, E maps to 65, and those are the same values that they have in ASCII. But we're not limited to ASCII characters anymore. So for example, here would be a valid Unicode string, and this contains here Latin, Greek, Cyrillic, Japanese, Mongolian, a snowman, and Arabic characters. And UCS2 decoding works basically just like it did with the other single byte character sets, except we look at 2 bytes at a time. So here we take the first 2 bytes, we combine them together, that gives us our code unit, our 16-bit code unit, and we see that's a 48, and we map it to H. And then we do that for each of these in the string. But this makes the assumption that the data is big-endian, right? If we send this and we send it to a machine that is expecting data in little-endian format, then it's going to misparse this, right? It's going to look at these and it's going to map them to the wrong code points, and then it's going to get gibberish. I don't know what these characters are down here, but they're not what we intended to send. So in order to solve this problem, the UCS2 character encoding allows for what's called a byte order marker. And it's this special code point FEFF. And so you can put this at the beginning of your string or text or file, whatever it is that contains the Unicode text. And this allows you to determine what the byte ordering is. So if you open up the file and you see that it starts with FEFF, then you know that the data is in big-endian format because the FE appears before the FF, and so you can read it as big-endian. Alternatively, if the bytes are swapped, if the data in the file is little-endian, then the byte order mark will appear as FFFE, and so you're able to know that the data is then in little-endian format. The intent was that big-endian UCS2 would be common, like the common one to be used. So on the Windows platform, which primarily runs on little-endian machines, little-endian is used. I don't know about all of the implementations, but little-endian, it turns out, is quite common today as well. So, advantages of UCS2. A huge number of characters are represented, right? The 65,000 characters, again, that's so many more than 256. Characters from different scripts are easily combinable into a single string, so we could not do that with the legacy single byte or variable length encodings because you needed different encodings to encode different scripts. Each code point is representable using a single code unit, so the encoding is still simple. You can still iterate over the 16-bit elements, and each element is going to be a single character. But it has some disadvantages too. So there's multiple possible byte orderings, so a byte order mark is required for interchange. Every character requires 2 bytes, so text in many languages requires twice as much storage. This includes English and Western European languages where previously we might have been just fine with a single byte encoding, and now by switching to Unicode, suddenly all of our text is twice as big, which is not a good thing. And then finally, none of the byte-oriented string functions like strcpy work with UCS2 strings because, as we saw in some of the examples previously, some of the characters may have 0 bytes in them, and strcpy is going to stop as soon as it finds a 0 byte. So we need a new set of string functions that would operate on 16-bit code units. So back when UTF 1.0 was released, this was the code space usage, so I copied this out of the Unicode 1.0 standard. The gray part is the allocated part, and the white part is the code points that were not yet allocated, so they were still available for use. This was in 1991. And indeed, in the Unicode 1.0 introduction, they declared that with over 30,000 unallocated character positions, the Unicode character encoding provides sufficient space for foreseeable future expansion. Or to paraphrase another famous phrase, 65,000 characters ought to be enough for everybody. So here's a graph. The blue line here shows the growth in the number of characters in the Unicode standard over time. So across the bottom we have the different versions of the Unicode standard. 9.0 is the most recent. It came out in June of this year. The red line is the growth of the number of distinct values representable in 16 bits over the same period of time. And we can see here that the integers aren't keeping up. Like, they are not pulling their weight here. They're not earning their pay. So that's a problem. So clearly we must have done something in order to support all of these extra characters. So we're now going to jump forward to today, and we're going to see what Unicode looks like today and how it's different from what it looked like in version 1.0. I'm not going to talk about all the evolution history because I only have an hour and I have like 90 minutes of content already. So it turns out we need to be able to encode more than 65,000 characters. So in Unicode 2.0, the code space was expanded to a total of 1,112,064 code points, though only a subset of that was usable for characters, and we'll see some of the details of why later. So we can't store that many distinct values using 16 bits, so the encoding has to change as well. Well, if 16 bits is enough space, how about 32 bits? So UCS2 is dead. We can now introduce UTF-32. So here we go. I've had to shorten our hello message to hi because I ran out of memory on the slide. And you can see that instead of reading 16-bit code units, we now have 32-bit code units. And again, each one of them just maps to a single code point, and then we can get that code point and convert it into whatever the character is. So here we'll read 4 bytes, and we'll see this is the value 48. Well, that's the code point 48, which maps to the H. Since this is also an encoding that requires more than 1 byte, we still have the byte ordering issue, but the same byte order mark works as worked in UCS2. So here, if we see FEFF, then we know it's still a big endian ordered text, and if we see FFFE and then 2 zeros, then we know that it's big or little endian UTF-32. But the great thing about this is, well, now we can encode characters that are outside of that lower 16 bits. So for example, instead of an exclamation point at the end, we could put this little bunny, which is, you can see it has code point 1F430, which is larger than you can store. It's 5 hexets, so you can't store that in a single 16-bit element. So, advantages of UTF-32. A huge number of characters are representable. Like if we were actually to use the entire 32 bits of it to represent a character, you could represent 4 billion characters. And I think that might be enough. We can't quite store that many, and we'll see why in just a moment. Another advantage, though, is that each code point is still representable using a single code unit. So yes, we do have to iterate 4 bytes at a time, but still each 4 bytes maps to a single character. It's not a variable length encoding. That isn't all that useful in practice, and we'll see why in the second part of this talk. But it's got a whole bunch of disadvantages, right? So there's still 2 possible byte ordering, so it still has that disadvantage from UCS2. Every character requires 4 bytes. We know we're wasting at least 11 bits per code point because, again, our maximum number of characters is about 1 million. But for English text or German text, we're actually going to be wasting 3 whole bytes out of every 4 bytes. Like now, our strings have exploded in size. And none of the byte-oriented string functions like strcpy work, just like with UCS2. And the last thing is very important. Nothing that was written to work with UCS2 works with UTF-32 anymore. So like all of the software that took early advantage of Unicode and UCS2 now does not work with this. So how are we going to solve those things? Well, there's a second encoding called UTF-8, and UTF-8 is a brilliant design. And it is a variable length encoding, so each character may require between 1 and 4 code units, which are bytes in this case, to represent. So here on the slide, if the code point, well, I'm not going to point. If the code point is representable in 7 bits, so if it's between the values 0 and 127, we're going to encode it using a single byte, and we're actually just going to store its value. So the X's here are the bits of the code unit here. So one of the neat things here is that all of those first 128 characters, those first 128 code points, those are the ASCII characters. And so what you'll see here is valid ASCII text is actually also valid UTF-8 text, which is a really nice property for interchange. It turns out those ASCII characters are also some of the most commonly used, right? Even if you're not writing, writing English text, you're still going to, generally you're going to have a lot of formatting information. So if you have HTML, you're going to have all the HTML tags, a lot of white space, maybe some angle brackets, things like that. And so all of those will still be encoded using only a single byte per character, so it's nice and compact. For characters that require, say, between 8 and 11 bits to represent, so between 80 and 7FF, we're going to split the bits across 2 different bytes. And so we're going to take the first 5 bits and we're going to put them in the lead byte, and then we're going to take the remaining bits and we're going to put them in the first trail byte. What you'll notice here is that we can distinguish between single byte and multi-byte code points here just by looking at the high order bit of that lead byte, right? If it's a 0, then we know this byte stands alone. It has no trail bytes following it. If it's a 1, then we know it's a multi-byte character, and so it's actually there's going to be 1 or more trail bytes after it. The other thing that's cool is that we can then count the number of leading ones in that byte, and it will tell us how many trail bits there are. So for example, if we have 1, 1, and then a 0 after the, well, if we have 2 ones, then we know it consists of 2 bytes. If we have 3 ones, then it consists of 3 bytes. If we have 4 ones, it consists of 4 bytes. So here's an example. Here's our ASCII text hello again, and we can see that we just map the values, and because all of these are representable using a single byte in UTF-8, they just map directly just like they did in ASCII. But of course, we can represent other scripts. So here's part of the string from earlier, and here's what it would look like in UTF-8. And then if we decode it using the UTF-8 rules from the table that we just saw, we map them to their appropriate code points and then to the characters. And we can see here that we can represent the rabbit just like we were able to do in UTF-32. And then finally here, I just wanted to highlight the fact that the lead bytes and trail bytes are disjoint. So we don't have the problem like we had in the Shift.JIS encoding, where when you're pointing somewhere, you don't know, am I pointing at a lead byte or a trail byte? We know, oh, I'm pointing at a lead byte, so this is the beginning of a character. Or no, I'm pointing at a trail byte, and you can seek forward or backwards, and you can find the next or previous character quite easily. So advantages and disadvantages of UTF-8. So advantages, ASCII text has the same representation in UTF-8, which is very useful. It's obviously a very widely used encoding. It doesn't require a byte order mark because the code unit is 1 byte, but there is an optional byte order mark, and it's this EFBB-BF sequence. If you want to know where that comes from, that's actually if you take the FEFF code point and you encode it using those rules we had previously, this is the sequence that you'll get out. So it's just the byte order mark encoded in the same way that all of the other characters would be encoded. Many of the byte-oriented string functions like strcpy, strcat will still work with UTF-8 strings because, again, they still have the single null terminator, and it's still a 1 byte code unit. And UTF-8 encoded text requires less storage than 16-bit and 32-bit encodings for most languages. And so this is a really advantageous thing. If we have English text, for example, it's going to be half the size than it was in UCS2. Disadvantages, it's a variable width encoding, so we can't just iterate over the elements of a std string containing UTF-8 text, for example, because, well, that's not going to give you the characters, it's going to give you just those individual code units. And finally, text for a few languages does require more storage than 16-bit encodings, and we'll see the list in a minute. So UCS2 is obsolete because it can't encode all of the code points. But many large systems and libraries were built using the 16-bit UCS2 encoding. So 3 big examples. Qt was built in 1992, which was before Unicode 2 was released that introduced this new encoding. Windows NT, which is now all of the Windows operating systems, development on that started in 1988. And back then, Microsoft said, yes, we're going to embrace internationalization and embrace this new Unicode thing. And so basically, the entirety of Windows is built around a 16-bit WCHAR type that used at the time UCS2. And then Java also uses 16-bit characters. .NET does the same, though that's largely because it was designed primarily for use on Windows. So we still need to have some sort of compatibility for these big systems, right? Like Unicode is a standards organization, just like the C++ standards committee in many ways. The big companies that are helping to build this standard are not going to be very happy if this standards committee puts together something that is impractical for them to move to. And so what we ended up with is this UTF-16 encoding. So for code points between 0 and FFFF, so any code points that are representable in 16 bits, UTF-16 is equivalent to UCS2. So those are exactly the same. This means that valid UCS2 text is also valid UTF-16 text. UTF-16 is a superset of the UCS-16 encoding. These are the most commonly used code points. So as the Unicode group has been adding new characters, they've been making sure that the commonly used things end up down here, so that we don't have quite as many things that fall out of that range, or at least not commonly in text interchange. So then, in order to represent things that are higher than that you can't represent in 16 bits, 2048 code points between D800 and DFFF are reserved for UTF-16 encoding. And so the code points that are too large to be encoded in 16 bits are encoded using these special code points in what are called surrogate pairs. So how does this work? So we take the code point and we subtract this base value from it, which will give us a 20-bit number, between 0 and then 5fs. We split the number in half, so we've got 20 bits. We have 10 bits in one half and 10 bits in the other half. The upper 10 bits are added to this D800 to form the lead surrogate, and then the lower 10 bits are added to DC00 to form the trail surrogate. So here we have a martini glass with some kind of drink in it, and it is code point 1F378, and so we can see how we can encode this in UTF-16. First, we subtract that base value to get our, our value within the range that we want to encode. We then convert it to binary just so I can show the 10 bits on each side. We split the 10 high order bits are in blue, and so those will form the lead surrogate. And then the 10 low order bits are in orange, and those will form the trail surrogate. We convert those back to hex just for simplicity, and we get 3C for the high order. We add it to that D800, and then we get the high order surrogate, and then we do the same for the low order surrogate. And so basically, when you're parsing UTF-16 text, if you find one of these lead surrogates, you then have to take that and the trail surrogate, and you have to undo this mapping, and that will give you the code point that is represented. So UTF-16, advantages. It has some level of compatibility with UCS2 and systems designed to use a 16-bit encoding, which is extremely important. So right there, like, the advantage is a good thing. And text for a few languages is smaller in UTF-16 than in UTF-8. But it's got a bunch of disadvantages. It still has multiple byte orderings, just like UCS2 had, so you still need the byte order mark. Every character requires at least 2 bytes, so we still have the problem that we end up with wasting a lot of bits. None of the byte-oriented string functions work, just like they didn't work with UCS2. It's now a variable width encoding, so we don't even have the benefit that UCS2 had, where, well, at least we've got 1 code unit per character. And then finally, binary string comparison for UTF-16 produces different results than for UTF-8 and UTF-32. So one of the neat things about the UTF-8 encoding is if you have 2 strings and you want to say, is this string less than the other string, if you just compare the bytes, you'll get this exact same result, true or false, as you would get if you were to compare the UTF-32 encoded strings as 32-bit elements. So that's a useful property for those, but unfortunately that doesn't apply for UTF-16 because we have to use these funny surrogate pair things to encode some of the characters. So encodings recap. UTF-8 is more compact than UTF-32. It's usually more compact than UTF-16. It's a variable width encoding, so it's a bit more complex. Again, you can't just iterate over the characters very easily. It's by far the most commonly used storage and data transmission encoding. So 2 years ago, when I first wrote this talk, 78% of the top 10,000 websites and 65% of the top million websites delivered their textual content using UTF-8. And it's the dominant character encoding on the internet. UTF-32 is simple, it's a fixed width encoding, but we're wasting tons of space, and so it's not really suitable for storage, either long-term or even in-memory processing in many cases. As for UTF-16, basically it just wouldn't exist at all today if we didn't have, if we didn't start off with UCS2. So it doesn't really have any advantages other than the fact that it provides that compatibility, which is important, but it's not a reason, to choose it. So, one of the problems, though, with UTF-8 is that for some languages, text is actually smaller when encoded using UTF-16 than UTF-8. And this is the full set of languages. This is one of my colleagues on the Windows team did some analysis. There's a text corpus online that has a whole bunch of sentences from many different languages, and he encoded them in both UTF-8 and UTF-16. And these are the set of languages that were smaller in UTF-16 than they were in UTF-8. And so you can see Japanese, for example, at the high end of the list, the text was 149% of the size when encoded in UTF-8 than in UTF-16, so it was 50% bigger. Now, if you're dealing with text in one of these languages, it might be very tempting to use UTF-16, and indeed, internally in your software, you might want to do that. But this is somewhat misleading, and it's misleading for 2 reasons. And the first reason is that this is only for dense text. So this is like if you have a novel that has no formatting information, nothing special in it, and it just contains characters in these languages. But like we said previously, that's often not the case, right? We'll have like HTML, which has tons of white space and brackets, and so that will dramatically reduce the difference here. The second is that both of these encodings compress about the same. So if you want to zip up content and send it across the web, the UTF-8 zipped content is going to be somewhat similar in size to the UTF-16 content, even when you're using these characters. And that makes sense because, again, we're encoding the same amount of data, it's just the encoding is somewhat inefficient, and so the compression algorithm should be able to take advantage of that. So one last thing about Unicode that we'll talk about before we start looking at how things work in C++, and that's dynamic composition. So even those 1 million characters are not enough. So here's the letter A. It's very simple. But maybe we don't just want the letter A. Maybe we want to have an accented letter A. And so the way that we form these in Unicode is through what are called combining characters. So for example, if we want to form the A with diareses, what we do is we take the capital letter A, which is code point 41, and then we follow it by this combining diareses character, 308, and then your text rendering program, whatever is going and actually rendering the text, PowerPoint in this case, should combine them together to give you the A with diareses. The A in this case is called the base character, and then the diareses is called a combining character. But you're not limited to one. So for example here, we can have the letter E and we can attach a tilde above it and an X above it, and then this little bridge below it. And then the text rendering software, if it's really good, it should be able to put these together. I tried doing this with the snowman, but I couldn't get PowerPoint to render the diacritics correctly on the snowman, so we're stuck with the letters. One thing to note here is that the order of these is sometimes important. So if two of the diacritics or two of the combining characters affect the same part of the character, then the order is relevant. So here, both the tilde and the X apply to the top side of the E, whereas the bridge applies to the bottom. So we can put the bridge wherever we like in this sequence as long as it follows the E. But if we put the tilde before the X, then the tilde will bind more closely to the E and then the X. If we put the X and then the tilde, then the X will bind more closely to the E and then the tilde. And so this does have some relevance. This character has no particular meaning, but in other scripts with other examples, with other more realistic real-world things, that would matter. So, Unicode types in C++. So in C++, we have some Unicode code unit types. For UTF-8, it's just char. Unfortunately, we don't have a special type to say this is a UTF-8 code unit. The reason for that is largely for compatibility with, well, basically everything that operates on single byte strings. For UTF-16 and UTF-32, we have char16 and char32. Note that I have not included wchar-t on this slide, and that's because the specification of wchar-t is basically the implementation does what it needs to do. On Windows, for example, it's a 16-bit type, because on Windows that's what the wide characters are. On most POSIX systems, I believe it's a 32-bit type. So, if you're using wchar-t widely, it's going to work differently on different platforms. We can also have Unicode string literals in C++. So here, for example, we can have, we use this U8 prefix to say this is a UTF-8 encoded string literal. We can use this \u inside of the string literal to say this is a Unicode code point. And so here we can say 2603, which is the snowman code point. If your compiler supports Unicode inside of the source file, you can also just put, for example, the snowman character right inside of the source file. And we can do this for char and char16t and char32t. The lowercase u and uppercase u are for char16 and char32 strings, respectively. We can also have Unicode character literals, sort of. And the reason I say sort of is because, well, not all of the Unicode characters are represented with a single one of each of these code units. So it is the case for char32t. So for example, we have the Latin letter X, we have the snowman, and we have this Martini class. All of those are representable using a single char32t, and so all of those are well formed. But for char16t, the Martini class will require two code units, two char16 elements, because it's not representable in 16 bits. And so the compiler will give you an error for that. And similarly for char, if we want to do UTF-8 encoded text, you're basically limited to the ASCII character set for these. All right, let's take a look at the amazing C++ Unicode string type. Yeah, okay. Well, we'll talk a little bit later about that, but we don't really have a great Unicode string type in C++. We do have std basic string, so std string. Std string just contains a byte sequence, and it sticks a null terminator on the end of it, so it can be used for storing UTF-8 text. Similarly, there's std u16 string and u32 string, which can be used to store char16t and char32t elements, just like there's w string for wchar-t elements. So here's an example of constructing those. We can just construct them from the string literals like we had before. There's really nothing special about this. But basic string has some problems. So you have to remember it's just a dumb sequence of code units. It's not code points, characters, text elements. All of those are higher level things that std string doesn't know anything about. So iterators iterate over those code units. If you have a std string that contains UTF-8 text and you want to iterate over all of the elements in it, well, you're not going to get all of the characters. So if you've got like a snowman in there, you're going to get each of the code units that was used to represent that snowman. Similarly, size does not return the number of code points. It returns, again, the number of bytes, the number of code units. And then functions like front, back, the subscript operator, etc. All of these just operate on code units. There's no higher level understanding in std string for Unicode. So here's a UTF-8 simple example. Let's say that we've got a string that contains hello, comma, space, and we want to say hello to a snowman. And so we try and we're going to push back a snowman. Well, that's not going to work because the snowman isn't representable in a single character. So what we end up actually having to do is we have to create a string that contains that snowman character, and then we have to insert it into the end, however many code units that required. We have to do the same thing for the U16 string, like if we want to push back the martini glass that is not representable using a single UTF-16 code unit. And it's only for UTF-32 that we can actually push back single characters consistently for all of the characters in the character set because all of them are representable in a single code unit. But again, most people aren't using UTF-32 in their software. So here's when things start getting tricky, as if they weren't tricky enough. Let's talk about string length. So in ASCII, this is really simple, right? So we've got this string that contains hello. I can count 1, 2, 3, 4, 5. All right, the length of this string is 5. Does anybody disagree with this? Okay, I'm just going to pretend like nobody disagrees with this, because the length of this ASCII string is in fact 5. What about Unicode? Well, this one I see 1, 2, 3. The string length of this is 3. Does anybody disagree that the string length of this is 3? Yes, all right, there are some people in the audience that disagree that this is 3. Well, maybe it's 3. It depends on what the meaning of the word length is. So here are the contents of this string. So we have the numeral 1, the letter A, the diareses, and then the martini class. And here is how it gets encoded into each of the character encodings that we've been talking about. So UTF-8, UTF-16, UTF-32. So if by string length we mean the number of bytes in the string, well, it's going to be 8 bytes for the UTF-8. You see I've colored alternate bytes differently. For UTF-16, it's going to be 10 bytes, and for UTF-32, it's going to be 16. If we mean the number of code units, well, that's also different. So it's 8 for UTF-8, which is the same as the number of bytes, because the code unit is 1 byte. For UTF-16, it's 5, which is half of the number of bytes, because we have 2-byte code units. And then for UTF-32, it's 4. If we mean the number of code points, well, now it's the same for all of the encodings, right? Because now we're talking about, okay, each of these code points may be encoded in a different way, but at least the string contains this one, the same characters in it. And so it's 4 for all of those. But alternatively, we might say, well, what if we want to know the number of text elements? So we want the 1, the A with diareses, and then the martini class, and that's 3. So that's different from the number of code points. So there's at least 4 possible meanings of this term string length. It might mean the number of bytes, the number of code units, the number of code points, the number of text elements. The number of code points is the same in all of the encodings. The number of text elements is the same in all of the encodings. For UTF-8, the number of bytes is the same as the number of code units, and for UTF-32, the number of code units is the same as the number of code points. So here, if we have a std string that contains this, well, this is UTF-8 encoded. So if we ask it for the number of, if we call s.size, well, it's going to give us the number of code units, the number of bytes. It's not going to tell us how many, characters are in the string. And then if we iterate over the elements of the string, again, we're iterating over code units, not characters. Well, if length is complex, how about equality? I mean, equality can't be that hard. So what is equality? So if we have 2 strings that just contain ASCII, we can think about representational equality, which is generally what we mean, and it's what the equals equals operator does for std string. So here we have A and B. They clearly have the same contents. If we ask, is A equal to B, then yes, they contain the same text. But it gets more tricky when we start dealing with Unicode characters. So here we have, this string that we've been dealing with so far. Are they equal? And it depends, because it turns out that some things in Unicode have multiple representations. So representational equality does not tell you if two different strings have logical equality. So to look at this example in particular, this A with diareses actually has two different representations. So we have the one that we've been talking about, where we just have the capital letter A followed by a combining character. But it turns out there's also a precomposed form of this that has the A with the diareses representable using a single code point. The reason for this is for compatibility with legacy character sets. So the Latin 1 happens to have this character, and so in order to enable a one-to-one mapping between UTF-8 or between Unicode and these other legacy encodings, oftentimes we have a lot of extra characters that probably should be dealt with in formatting software, not in the character encoding itself. So here we can see we've got a decomposed form is what we call the first one, and then a composed form or a precomposed form is the second one. Turns out even the letter A has two different representations. So we have the Latin capital letter A, and then we have a full-width Latin capital letter A, which is used when you're trying to render the Latin alphabet and CJK characters in fixed width, and you want the Latin characters to take up the same amount of columnar space as the CJK characters. We also have multiple representations of, say, this, for example. So we actually have a Latin small ligature FI. Should that be considered exactly the same as an F followed by an I? Maybe. Roman numeral 12, totally you don't want to type XII, so we've got one character for that. This is also for compatibility with some legacy character encoding. But even if we ignore all of those silly things, we still have the problem that because of combining characters, we have multiple representations of complete characters. So here, for example, we have this equal sign below and the circumflex accent, and they apply to different parts of the character. So this character can either be represented in either of these orders, and it's the same thing. So Unicode defines two types of equivalence. The first example here shows canonical equivalence. So if we have the A with diareses, the precomposed form, it is canonically equivalent. It should be treated exactly the same for equivalence purposes as the capital letter A followed by the combining diareses. The second two examples here are for what is called compatibility equivalence. So for example, there's this single character for a combined L and J, and then obviously you could have just separate letters L and J in your text. And then the third example, we've got this 1/4 fraction, and that could be considered in some cases to be the same as 2 followed by 1 followed by a slash followed by a 4. And you might say, well, why would I ever want those to be considered equivalent? And I'll tell you, if you're writing the search engine for a web browser, you really want LJ to match either of those regardless of what's in there, right? Because your user is going to expect it's going to match, this thing. It's going to match ligatures. It's going to match this 1/4 fraction. Otherwise, your search isn't going to be particularly useful. So both of these are useful in different cases. So Unicode defines 4 different normalization forms. It first has canonical and compatibility forms, so that depends on which kind of equivalence is used during the normalization, and then composed and decomposed for each of those. So that's whether when normalizing it prefers the composed form or the decomposed form. And the normalization also includes a well-defined ordering for the combining characters. So like we had the example of the A with the 2 different combining characters, there's a well-defined order of which order those should appear in. So how do we do normalization using the C++ standard library? You guys should know what's on this slide already because it's basically just this for everything. You can't do it with the standard library, but we'll see in a minute how we can do it with other libraries. So we'll look at another fun example, ordering. This ought to be fun. So if we have 2 strings, we can ask is A less than B, and that will in this case say yes, and so A is ordered before B. And we can do the same thing for Unicode characters. So here we've got 2 UTF-8 strings with different characters in them, and we can check if they're ordered. But what does that mean? So let's look at a sorting example. So here we've got a vector. It contains the letters C, X, B, Y, A, and Z. And we're going to use std sort to alphabetize the strings, and then we're going to print out the result. How many people here think that that is what this is going to do? How many think this is not what this is going to do? How many people are not sure? Okay. Yeah, so the result here is going to be X, Y, Z, A, B, C. Why is that? Well, because std sort is just going to use the default comparer, and so it's going to compare these the code points, not the actual characters in some sort of alphabetization factor. So alphabetization is a property of a language, not of the text encoding. So here, X, Y, and Z have code points that are lower. So if you look at the ASCII table, they appear first, and then the lowercase letters appear second. So that's why they get sorted in this way. In order to alphabetize, we have to do what's called collation, and that requires a locale. So for example, if we sort using the English locale, then we get the alphabetized result that we're looking for. The reason that you need a locale is that the order actually depends on the language, the locale that you're using. So for example, if we use the German locale, and we have this new sequence of strings, Z, the A with diareses, the B, and the A with diareses is just going to be treated as an accented letter A, and it's going to appear in the alphabetization after the unaccented letter A. But if we use the Swedish locale, that's actually a different letter in its own right, and so it gets collated after Z. So ordering and sorting is very locale dependent. So Unicode collation in the standard library. This is also left blank. So full collation in the standard library is not fully supported. Some implementations may support Unicode locales. Not all of them do. Locales are a very implementation-specific thing. But we'll look at how we can do this in a portable way. I'm going to skip this next section just so that we can get to the more interesting things while we still have time. So international components for Unicode. The ICU library is the library for Unicode. So the C++ standard library is missing a lot of important Unicode functionality, but the ICU library has basically everything you could ever want to do with Unicode strings. It's got a huge set of features, more than you'd ever need, I would expect. It's very widely used, so it's well tested in a lot of real-world software. It runs on many platforms, has a permissive license. Unfortunately, it has its own string type, Unicode string, and unfortunately it uses UTF-16. It doesn't work well with other string types, like std_string in most contexts. It's not modern C++ by any definition of that term, and so the reason for a lot of those downsides is that it's based on a legacy, an old C++ library, which was ported to Java, and then was ported back to C++. So it's not exactly idiomatic modern C++. ICU also has a lot of features for general internationalization stuff. We're not going to talk about those here because this is a talk on Unicode, not internationalization. So here, for example, it has this uchar32, which is a 32-bit UTF-32 code unit. It also has a uchar, which is a UTF-16 code unit. The reason why UTF-16 is the character set that it uses internally is because, well, or the encoding it uses internally is because that was what Unicode was back when it originated. And then, of course, it was used in Java, which is UTF-16 based. We can also see here that we can use uchar, which is the UTF-16 code unit, and we can use char for our UTF-8 encoded things. It allows conversions between these encodings, so you can use this from UTF-32 to construct a Unicode string from UTF-32 text. We can use from UTF-8 to do the same for UTF-8 text. This Unicode string type has a whole bunch of operations, just like we would expect a string type to have to do comparisons. It does, it has a whole bunch of Unicode-aware operations. You can also do normalization using ICU. So here, for example, we construct a normalizer to normalize into NFC, which is the precomposed form. We can then construct a string that contains the decomposed A with diareses. And we ask this normalizer, well, is this in normal form? And it'll say, no, it's not, because this is a normalizer for the precomposed form. And then we can call the normalized function, which will return us the Latin capital letter A with diareses, which is the precomposed form. You'll note here from just a modern C++ standpoint, so we return our status via a status out parameter. We return our result as an out parameter. Those were totally reasonable things to do back before we had move semantics and exceptions, but maybe not the most modern thing nowadays. We can also do collation, so it has its own locale library. So here we can construct an EN-US locale and compare strings. It has Unicode regular expressions. So here we construct a regular expression matcher using this for Unicode. So here this regular expression will match numeric characters. And so we can pass in this string that contains the Roman numeral 12 and the 5/8 fraction, and it will match both of those because both of those are numeric characters. You would be unsurprised to learn that the C++ locale or the C++ regex library probably won't do that for you. So ICU is not very modern C++. Boost also has a locale library and a regex library. Boost Locale was interested in Boost 1.48. It's a modern C++ API, and it can use various backends, so it can actually use ICU under the covers. So you still get all of that well-tested, well-supported functionality. It can use the C++ standard library if you wanted to do that, the POSIX locale APIs, the Windows APIs. Boost Locale is nowhere near as feature-filled as ICU, but it supports the commonly used things that you might need to do with text. So Boost Locale, you basically construct a std locale using it. So here, for example, we construct an enus locale with the UTF-8 character encoding. I'll note that this is very useful if, for example, you're working on Windows, because on Windows, the C++ and C standard library locale implementations do not today support UTF-8. We can do normalization. So here we have both the precomposed and the decomposed forms of that A with diareses. And we can normalize those into the opposite form and then see that we get the correct result. You can see this is much nicer from a modern C++ perspective, right? We actually return the result. We throw exceptions on out-of-memory errors and things like that. Collation is supported, so there's a Boost Locale collator facet that gets imbued in, or gets put into each of these locales, and we can use that for comparisons. You'll see here that it has this primary argument into the comparison operation. So Boost Locale actually supports all 5 of the Unicode has 5 different comparison levels as to whether or not case and accents and punctuation are taken into account when doing comparisons. So you have full control over that. ICU will do this as well. Conversions, it's got this nice UTF to UTF function, which will allow you to convert from one UTF encoding into another. More importantly, it'll also allow you to convert from legacy encoding. So for example, here we have that Russian hello string, and it's encoded in the Latin Cyrillic encoding. And we can use this toUTF function, and we can pass in the name of the encoding that it's encoded in and convert it to Unicode. So if you're dealing, if you're writing software that needs to deal with, old files or things like that that are encoded with different encodings, you can do that easily this way. It also provides string-based case manipulation functions. So for example, toUpper, toLower, toTitle. The C and C++ standard libraries provide functions like this, right? Like isAlpha or toUpper. But they operate on single characters, and those are generally not suitable for Unicode text because, well, each character may not be representable in a single byte or a single code unit. And moreover, there are some characters that when you uppercase them or lowercase them, they turn into 2 characters. We can also do boundary analysis with the Boost Locale library. So here, for example, we have this subject string, which is the one we've been looking at so far. And we can say, all right, I want to have iterators that iterate over over all of the characters in this string. In this use of character, they actually mean text elements, so that A with diareses will be treated as a single thing. And so if we ask for the size of the string, it's going to say 8. This string is encoded using 8 bytes. But if we iterate using this segment index, this Boost iterator that is created, we'll see that the result is 3. There's only 3 elements in there. And so this actually is what allows you to iterate over individual characters in the string, which is very useful. All of this is very extensible. You'd have to consult the documentation for details. There will be a link at the end. Finally, there's Boost regex, which also provides similar functionality to the ICU regex. I don't know if it's comparable or if it's less. I haven't used it extensively. But here, for example, is how we might construct a regex that matches numbers, and then we can match those numeric characters that aren't actually numbers. There's been a few proposals for standardization to add some better Unicode support to the C++ standard library or to C++. Obviously, like the fact that we've gotten this char16t and char32t and the Unicode string literals and character literals, like that's a big step forward. But again, we're missing all of this library functionality that we would really need. One of the proposals from a few years ago was to retrofit some new features onto existing standard library stuff. So to, for example, add support for more easily character encoding and conversion iterators for converting between encodings. Another one was actually to produce a new encoded string type, which would allow you to specify the encoding with the string. I would make a joke that that's exactly what C++ needs, is yet another string type. But on the other hand, this may actually be a case where we need something new and better just to deal with Unicode better. And then finally, this was a more recent proposal from late last year or early this year, And it proposed some new conversion functions to the standard library, similar to those UTF to UTF conversions that we had in the Boost library. Here's a bunch of resources. I will be sharing the slides, so don't worry about that. And with that, I have run out of slides. So, happy person raising one hand. Are there any questions? No questions. Oh, yeah.
Related to the bit masked order, especially on Windows, there are situations when the files don't have this flag. And then, for instance, if you are loading this file, you don't know what kind of encoding this exists. So what kind of approach do you think the viewers are handling in background in order to display correctly and also an optimized way, probably Boost normalization or
so I believe the question is,
for Windows.
So let's say we have files that don't say what encoding they're in. How do I guess what encoding they're in?
Match.
Yeah, so there's techniques using heuristics that you can use to figure out what's in that file. So for example, if you want to determine, am I a file that's encoded in UTF-16, little endian, oftentimes there'll just be a lot of 0 bytes, and so you can kind of guess, all right, this is probably a UTF-16 file. Similarly, for the different ISO IEC encodings that we looked at earlier, you can do statistical analysis on the characters that are present and figure out which ones, what you think the character encoding might be. I know there's some famous, YouTube videos where someone types a particular English string into, a file, closes it, opens it back up in Notepad, and Notepad's like, oh, this is some other encoding because, it's misjudged, it's analyzed the file. To do this, ICU, I believe, does have have functionality to do that guess for you, to try and guess what the encoding is. I know that on Windows we have several functions. I forget what they're called. I could get them to you though. That will give you an estimate of what we think the encoding is. And then from that point, once you have a good guess, basically you got to show it to the user and say, does this look right? And that's actually what I believe what Word will do. It'll actually pop up a dialogue is this the encoding you want, or is this how you want it decoded? In some cases.
I was thinking that there is a specific, very well-known by some guys way to find this way very fast. I mean, without following the whole content of.
Yeah. So even those techniques I described, they don't actually need to look at the whole content. So if you want to identify UTF-16 text, oftentimes you only need a few characters, and you can say, okay, I've got a non-zero byte, and then a 0 byte, and then a non-zero byte, and then a 0 byte. But for other ones, it depends on the actual content of the text, and then the actual encoding that was used.
Yes, basically your pictures you had shown how you detect the UTF-8. Basically, applying this idea, you can find by iterating over 10 characters. It's enough, I think, to detect this.
Yeah, and actually UTF-8 is fairly unique. It's not similar in any way to many different encodings, so it's actually pretty easy to determine if you have UTF-8 text. Yeah.
Hi. You showed a sort, a call to sort, and you passed locale as the comparison function. So that means the locale acts as a comparison function object.
Yes, so the std locale objects actually have a function call operator that uses the collation, I forget which facet it is, but one of the facets does collation, and that does that, yes. So you can actually pass a std locale to do collation into std sort. All right, well, thank you all for coming. I'm here the rest of the day. Feel free to come up now or whenever, and I'm happy to chat.